Hi guys, it's Lutfi here. Hope you are doing well. In this video, you will see how we can perform the deployments and simulation of 5G network functions in the Red Hat OpenShift local cluster environment. For the container environment, we will install and set up the Red Hat code-ready containers in our laptop or desktop to create the Red Hat OpenShift local cluster. For the 5G deployment and simulation, we will use the Open 5G software to emulate the 5G core functions, and we will use the UESIM run software to emulate the G-Node-B and UE function. Now let's get started. The Red Hat Code-Ready Containers, or CRC, is a platform that provides a minimal pre-configured OpenShift cluster version 4 to be installed in our laptop or desktop for testing and development purposes. It has minimum system requirement for virtual CPUs, 8 GB of memory, and 35 GB of storage space. In this simulation, we will install the code-ready containers and the virtualization software on the Ubuntu operating system. The code-ready containers and the QVM software will then create the CRC VM to host the OpenShift cluster. Once this code-ready containers virtual machine has been created, the CRC will create and set up the single node OpenShift cluster consists of Kubernetes, master node, and worker node. The CRC will also set up the kubelet process, the container runtime, and the kube proxy on top of the worker node. Once this single node OpenShift cluster has been set up, we are ready to deploy the 5G pods, consists of 5G core pods and the 5G G-Node-B UE pod.
Okay, now let's try to install the code-ready containers or OpenShift local in our PC. Here we are using the Ubuntu operating system. If we check, the version is Ubuntu version 20.04. We have prepared also the deployment scripts and the code-ready containers installation files. We got these two code-ready containers installation files from the Red Hat website. This is the web page that we can download the installation files to be installed in our laptop. You can just click this install OpenShift on your laptop, and it requires Red Hat account credentials to log in. If you don't have one, you should create it first. Okay, now we are in. As you can see here, there are several options for the OpenShift cluster to be installed. We can install it on cloud, we can install on data center, or we can install on our local PC. Here you can get the installation files by just clicking the download OpenShift local button. And we have also several operating system options for the installation. We have Linux, Mac OS, and Windows. We can get also the secret files for the code-ready containers installation. Just click this download pull secret button, or you just can click this copy pull secret link to to be pasted in your console. In this page, we can also get the documentation on how to install the OpenShift local. By clicking this link, you will get the starter guide downloaded on your computer. Okay, now back to the console. We have the CRC Linux tar files as the code-ready containers installation file. We just need to decompress that file using tar-xvf and file name. Okay, done. Let's have a look inside this folder. We have the CRC file and also the license file. We will move this CRC file to our user local bin directory. So it can be executed from any location. Okay, let's try to execute this CRC application by giving command CRC version. As we can see here, the CRC version is 2.24. The OpenShift version is 4.13.6. And we have also the Podman version, which is 4.4.4. Now we are ready to set up the CRC environment. We will do it by using this command, CRC setup. And the setup is done. We can start the CRC instance using CRC start command. And we need also to include the secret files. This command will take approximately 15 minutes or more, depending on your memory and virtual CPU configurations. This command will start the CRC instance, create the CRC virtual machine, set up and create OpenShift cluster and Kubernetes container environment. Let's start it. Okay, now the CRC virtual machine is running. Starting Kubernetes service, and we have the progress now is waiting until the user secret is written to the disk. This will take a while. Okay, now it's starting the OpenShift instance. Okay, now we have the progress. 4 operators are progressing. Now all operators are available. It's checking the stability. Okay, now the code-ready containers is ready. The OpenShift cluster is set up, and we can try to log in into the OpenShift cluster. We need to give this command to be able to use the OpenShift cluster. We can log in first as cube admin user. Okay, we are in. Now we can check the status of Kubernetes is ready with this cluster IP, and it's listening to 443 port. And we have also the OpenShift service is ready with this domain name. You can check also the node status. Here we have the single nodes for the OpenShift cluster. The roles are control plane or master node, and also the worker node. Here we have the Kubernetes version 1.26. Now let's create the new project using the developer user. The command is oc new project and the project name. Let's check if this project has been created. Okay, as you can see here, the 5GNet project status is active. And the next step is to create the service account for the deployment. We have already the script for the service account creation. Let's have a look inside the script. The kind is service account and the name is developer SA. Let's try to apply this service account script. Okay, service account created. You can check by command ocget SA. You can see here the developer SA service account is created. And we need to grant some policy to this service account. We need to log in back as kube admin user. The first policy we can grant to this user is ANYUID, and the second policy is privilege. Okay, policy has been granted. We can log in back as user developer. So now we are ready to make the deployments of 5G core networks. We have already the deployment scripts here for the all necessary function. After the OpenShift local cluster has been set up, we are ready to apply the scripts for 5G core network deployment. These scripts will make pods and services for all 5G basics functions. If we have a look at one of the deployment scripts, it will have a kind deployment and it will use the service account name developer SA. For the pod creation, it will use the pre-configured Docker Hub image, and after the pod has been created, it will execute a command as an application script inside the pods to enable the 5G network function. For the service script, it will set the predefined cluster IP, and it will also set the port assignments for each 5G network functions. Okay, now we are ready to apply the scripts for the 5G deployments and services. We will apply the scripts for the services first. As you can see here, all 5G functions services has been created. Let's check via OC get SVC. Okay, this service has been created. Its cluster IP has been set, and also the port has been set as well. The next step is to apply the script for the deployments of the pod. OC apply -F deployments. Okay, deployment scripts has been applied. We can check via OC get all. You can see here the pods has been created for all 5G network functions, and the deployments already created, also the replica set for each 5G network functions. Okay, let's check for each 5G network function pod. First, we would like to check the AMF or access and mobility function. Let's log in into that pod. Okay, we are in. We can see here the process that's currently running is the AMF application script that will enable the AMF function and open the NGAP port for listening. You can see here the port that is listening is 38412 for NGAP protocol. So it's waiting for the connection request from the G node B. Also for the SPI port, it is listening and the SPI connection has been established to the NRF function. So it can communicate with NRF via these ports. Okay, next we want to check as well the authentication server function. Let's check the process is currently running. Okay, the authentication server function scripts has been running and it's also listening to SPA connection via this 7777 port, and the connection from the authentication server to the NRF or network registration function has been established. Let's check next network function. Okay, we will check MongoDB. Okay, these are the process currently running in MongoDB pod. It start the MongoDB database with referring to the config file mongodb.conf, and it was listening via port 27017. As we can see here, there are some active connection that's established to the UDR network function. Let's check. Let's check the endpoints of each network function. Okay, this connection is between the MongoDB and the web user interface. So it has been established between the MongoDB and web user interface pods. So let's check the next network element is NRF or network registration function. You can see here the process of the NRF scripts has been running, and also it has listened via port 7777, and the connection to the other network functions also has been established. Let's check as well the SMF. The process has been running, and it's also listening via port 7777 for SPA connection, also listening via UDP ports here for the data connections. Next is UDM or Unified Data Management. Okay, the UDM scripts, UDM application script has been running, and the ports the connection to NRF as well is already established. Next, we want to check the UDR or Unified Data Repository, which is the back end of the UDM. We can see that the UDR application script has not been running. Let's run manually. So for the ports also not yet listening. Let's check the configuration first for this UDR. Okay, here we have the connection string for the database. So it's connecting to the MongoDB service IP database, and it's listening via port 7777 via the ATH0 interface, and it also connect to the NRF address and port. So let's run the UDR script. Okay, the script has been running. Let's check. Okay, it's listed here that the UDR script has been running, and also let's check the port. Okay, the ports also has been listening, and the connection between UDR and the MongoDB database has been established also with network registration function. Okay, we're done with UDR. Let's check next pod is UEGNB. Okay, within this pod, we haven't execute any scripts in the deployment script, so we will execute the scripts manually to establish the NGAP connection between GNB and the AMF. It's not established yet, the NGAP connection. And also, we will start the UE emulator here to simulate the registration request to the 5G core network. Okay, next network element is UPF, or user plan function. Okay, the UPF, or user plan function application script, has been running, and it is listening via these two ports, 8805 and 21552, the UDP ports. The last pod we will check is the web user interface pod. Let's see the process currently running. Okay, this script is currently running, and it's listening via port 3000. Okay, this port will listening the request to open the web user interface via browser, and the ports to connect to the MongoDB is already having the connection established, so that's okay. Hi, in this part of video, I want to show you how we simplify the way we interact with the OpenShift object via the web page. This feature called the Web Console, or CRC console. Let's open the CRC console through this command. It will open the default web browser to display the login page of the web console. It's required us to fill in the credential for the OpenShift cluster. We will use developer user. Now we are already inside this CRC console or web console. We can see here there are many options that we can do to visualize, manage, and access the OpenShift object. The first feature is topology. We can access easily the pods from this topology map, and we can manage easily every single pod exists in this topology map. The other feature is observe. Actually, here we can monitor the cluster. We can monitor the CPU utilization, the memory utilization, also the CPU usage. But we have to activate the cluster monitoring, and it will consume more memory or random access memory that we allocate for these code-ready containers. So in this case, I have disabled the cluster monitoring, so we cannot see any utilization here. So we also can create and manage the build configs here. Also in here we can create the Helm chart and repositories. Also we can create the config maps and secrets. And in projects, we actually can see the whole OpenShift object for this project, the 5GNet project. We can see here the deployments, the pods, the services, and other objects under these projects. To access the pods, we can click in the pods part, and you can see here the list of pods for this project. And to access the single pod, just click the pod name here, and if you want to see or access the console inside the pod, you just click the terminal and we are already inside this pod. From the topology menu, we can create the nice topology here for the 5G core network, and we can also draw a line between two 5G core functions to visualize the interaction between the pods. For example, here between the UEGNRB pod and EMF pod, we can draw a line so we know that the UEGNRB pod will request something to AMF pod, and AMF pod here act as a server. We can also draw multiple lines from each pod So we know the interactions from each pod to the other pods. Okay, that's the pretty much the interaction between 5 core network pods. And to access easily inside the pods, just click on the pods, and on the right panel, we click the pod's name and access the terminal here. In order to perform the UE registration simulation, we need at least one subscriber exists in subscriber database. We will check in our MongoDB database if we have any subscriber. As you can see here, we have no subscriber currently in subscriber collection. So we have to create one subscriber to perform this simulation. As you can see here in the OpenShift service list, we have the web user interface is listening at port 3000, and the node port is listening on port 30,177. Let's try to access the web user interface web page. Okay, this is the login page of the web user interface. It needs credentials to enter the web user interface. The user is admin and the password is 1432. One, four, two, three. Okay, we are already in. In this web user interface, we can add subscribers We can also make a profile to be able to use by the subscribers. So we just need to add a subscriber here. We need to define the IMSI. And we need also to change this type to IP version 4 only for the APN configuration and capability set to enable. That's it, and we save this subscriber. We can check from MongoDB database if the subscriber has been saved into the database. As you can see here, we have already created that subscriber in the database. Now let's access the G-Node pod to be able to emulate this simulation. In this directory, we have the entry point script, also the G.B YAML file, and also the UE YAML file. These YAML files have been generated by this entry point script to make the provisioning of GNB profile and UE profile. As we can see inside the G.B YAML files, we have set the MCC to be 1901 and the MNC is 2070. And we have also set the link IP, the NGAP IP, and the GTP IP. We set also the address of AMF configurations. This is the service IP of the AMF. And also the NGAP port, which is listening to the request from the G.B. In the UE YAML files, you can see the configuration for the user equipment. Here we already set the IMSI to the one which we register in the MongoDB database. And we have also the same MCC and MNC which we set in the G.B. We have also set the key and operator variable the same with the one in the MongoDB database. Okay, now let's try to emulate the G.B function from this G.B pod. But before that, we can set the sniff tools that can capture the message from and to the AMF pod, so we can see online what messages are sending out and received by the AMF pod. The command is ocsnif, the AMF pod name, and the namespace name. Okay, the Wireshark has been opened, and we can set here the filter to be ngAP only, so we can identify directly what's happened in N2 interface between GNB and AMF. Okay, let's try to emulate the G node B. We emulate the G node B by using this command nr G node B, and we use option -C to point to the configuration file. Okay, now it's already established the ngAP, the N2 interface, the N2 connection between GNB and AMF. We can see from the Wireshark there are ng setup request and ng setup response. We have the successful outcome for the ng setup response. Let's try to do it one more time with the process running in the background. So after the GNB is already up, we will use the UE emulator to emulate the request from the UE to the 5G core network. We will use this nr-UE file to emulate this registration process. The command is nr-UE. We use also -C option to point to the configuration file, the ue.yaml file. We will try to see the message appears after we execute this command. Okay, we have new message coming in the Wireshark. Okay, now let's analyze the trace from our UE registration test simulation. At the beginning of the trace, we can see the ng setup message between G-Node B and the AMF to establish the NGAP connection between them. The G-Node B send the ng setup request message containing the information about the global G-Node B ID, the G-Node B name, and also the information about the tracking area code, including the element identity, also the slice information. The AMF then replied back with the ng setup response containing the confirmation about the successful ng setup message. Also, it sent the information about the AMF name, the global unique AMF identity, the AMF relative capacity, and also the information about the slice. After NGAP connection has been established between G-Node B and AMF, we have tried also the registration request, and inside this initial UE message registration request, the UE actually send the registration type is initial registration, the UE mobile identity, in this case is subscriber unique concealed identity, which contains the IMSI number of the subscriber, consists of MCC, MNC, and also MSIN. It also sends UE security capability and also user location information. Once this request has been received by the AMF then will contact the authentication server function to request for authentication information request for this particular subscriber. This message has been sent via the SBI interface to the authentication server function. So that's why the protocol is HTTP. The authentication server function then replied back with the data for this authentication information. As we can see here in the data frame, the authentication server function actually replied back with the authentication data consists of the random number, the encrypted res value, also the authentication number. Once the authentication information has been received by the AMF will send the authentication request to the UE to challenge the UE for the authentication response. The UE then send back the REST value in the authentication response to be checked further by the AMF and authentication server function. Once this REST value has been received by AMF will send this REST value to the authentication server function to be checked. In this case, the authentication server function has successfully checked, and the result is, we can see here, authentication result is authentication success. Means that the UE is authenticated to connect to the 5G network. The next step, the access and mobility function, or AMF, will send the security mode command to the UE to confirm about the security algorithm will be used in this connection. The AMF also send the email SV request for this connection. So then the UE will reply back the security mode message with the confirmation of the security algorithm will be used. This message is encrypted here in the reply message by the UE. Once this okay, and the authentication and the security message, the AMF will send the request to the Unified Data Management, or UDM, to query about the subscriber data information from UDM. The UDM then will reply back with the subscriber data that is stored in the UDM. As we can see here, the information include the subscribed UEAMBR, the uplink and downlink, for the particular subscriber. The RAT type information also sent back to the AMF. Okay, once the information about the subscriber has been received by AMF, the AMF then will send the initial context setup request to the UE engineer side to set up the context by sending the necessary information for context creation, including the connection ID and also the aggregate maximum bitrate for downlink and uplink, the global unique AMF identity, the slice information, and also UE security algorithms and other security data. The UE then replied back with the confirmation for this context creation. Once the context creation has been success, the AMF then will query to the network registration function the information about the target session management function to handle the session creation. The NRF or network registration function then replied back with the information about the session management function, especially the IP address of this SMF. Once received from the NRF, the AMF contacted the session management function for the session creation. The AMF sent the maximum data rate, the PD session type, the capability of the UE, and also the address of the connection. The SMF then reply back with the necessary information about this session creation, including the QoS rules, the session AMBR, the PDU address of the UE, the QoS flow description, and other necessary information, including the DNS and DNN or APN. Once this session has been created, and the AMF will send the PDU session resource setup request to the UE side and GNOD side to set up the resource for the bearer creation in the radio side. Once this request received by the UE and GNOD, the GNOD will reply back with the PDU session resource setup response containing the information about the connection ID for this bearer. Also, it sends the associated QoS flow list for this bearer creation. That's the general idea about this trace. It's taken from the UE registration test. This is the end of our video. If you find this video useful, please share to your colleagues, and please feel free to leave the comments or questions in the comment section. Thanks for watching, and see you on the next video.